Dear students, Assalamu alaikum and welcome back to Plant Physiology course. In the previous video, we discussed osmosis and it was an introduction to osmosis. So let's continue on that and discuss more about osmosis. Before revisiting the concept of osmosis and more discussion about osmosis, let's consider a few main points or important concepts as far as solutions are concerned, because osmosis is mostly the movement of molecules from the region of higher chemical potential to a lower chemical potential, and in the most part solutions are concerned. So if we have a container or a cell or whatever it might be and we have a semi-permeable membrane, so mostly there are solutions on both sides. So for example, we have solution A and solution B, and this is a semi-permeable membrane. So let's consider something about solutions, and these concepts will help us a lot as far as the discussion of osmosis is concerned. So solution, we all know it's dissolving solute in a solvent, but as far as the kinds of solutions is concerned, theoretically there are 9 possible types of solutions, keeping in view that which one of the 3 states of the matter is solvent and which one is the solute. So 9 possible types of solutions. So if we take for example solid as a solvent, then we have solid in solid, and then we have liquid in solid, and then we have gas in solid. And similarly, if we take liquid as a solvent, so we have solid in liquid and liquid in liquid and gas in liquid. And if we take gas, for example, as a solvent, so we have solid in gas and liquid in gas and gas in gas. We are not going to discuss all these types because this is beyond the scope of our current discussion. We are interested in these solutions in which a solid is dissolved in a liquid solvent. So solvent is liquid and the solute is, for the most part, it is solid. And in osmosis, we mostly discuss these types of solutions and the movement of molecules from a higher chemical potential to a lower chemical potential. As far as the plants are concerned, we know that the solvent in the plant is water. So our discussion will be mostly about aqueous solutions. Aqueous solutions, solutions of solids in water or liquids in water. It might be gas in water, but mostly it is solid in liquids or solid in water. Aqueous solutions is our main concern at the moment. From the standpoint of the chemical potential or the free energy or the considering the second law of thermodynamics, so what happens when a solution is made? So we have a beaker of water again, and we dissolve some type of solute in it. It contains distilled water, and we are dissolving, say, sucrose, and we are making, say, a 10% solution of weight by volume. So 10 grams of sucrose in enough water to make 100 ml of solution. So it's sucrose dissolved in it, and so these are the sucrose molecules. Now what happens when we make the solution, when we take the solvent and add solute into it? We know that water is a polar solvent, and only polar molecules or polar solutes, they can be dissolved in water. Non-polar solutes, they do not dissolve in water. For example, if you take a few ml of oil, whatever the oil might be, whether it is canola oil or it's olive oil, whatever it might be, and you add it to the same beaker or a glass of water and no matter how long you stir it and try to dissolve it, it will never dissolve into it. And whenever you stop stirring it, when the agitation stops, all the oil droplets, they coalesce, they unite, and they form a thin layer at the top of the surface of the water. So, since oil is a non-polar compound, you cannot dissolve it. Similarly, if you take a spoonful of sand, clean sand, you have washed it, it's clean, and then you add it to a glass of water and you try to dissolve it, you cannot dissolve it because it is not soluble in water. So only those molecules which are polar, they can be dissolved. So one of them, for example, it is sucrose. Similarly, if you take a very common compound which we use in our daily life, sodium chloride, the common table salt, NaCl, and when you dissolve it, it gets dissolved in water, in distilled water or whatever it might be. So what happens when a polar molecule is dissolved in water? Water is a polar molecule, and we know that water has two ends as far as the structure of the water molecule is concerned. So we have on one side oxygen, which has a partial negative charge, and on the other side we have two hydrogen atoms with a partial positive charge. So water is a polar molecule and it has two ends like this. One is a negative end and other is a positive end. It's a polar molecule. So when a polar molecule is dissolved in water, what happens that water molecules, they form hydrogen bonds with that molecule. So positive ends of the molecule, they make a weak bond with the negative end of the molecule, and other water molecules, for example, on this side with a negative end, they bond to the positive side. So a single polar molecule is surrounded from various sides the water molecules. In other words, a single solute molecule is surrounded by several water molecules, and when these water molecules make weak bonds with the solute molecules, now these are hydrogen bonds. When this bond formation takes place, what happens that all these water molecules, in this case there are two molecules, and these molecules now they are bound to that particular solute molecules. And what's happening that when solution is forming, the process of solvation, the number of free water molecules, it decreases, the number of free water molecules. And when the free molecules, their number decreases because they become bound to the solute molecules. And once they are bound and number of free molecule decreases, what happens that the chemical potential of the water also decreases because it is also affected. Chemical potential or the free energy, it depends upon the free water molecules. What I wanted to explain or to let you know or to tell you that when the solution is formed, and it depends upon the strength of the solution, or it depends upon the concentration, the quantity of the solute, what happens that the number of water molecules, the free water molecules, it decreases. So the free energy or the chemical potential of that particular water, whatever the quantity might be, it decreases as well. Now we have two beakers of water. And it contains pure water, just to illustrate the concept. And this particular beaker, it contains solute, whether it's sugar or sodium chloride, whatever it might be. And there is a certain strength of the solution, say it is a 10% solution of NaCl. Now, this is pure water, and what we mean by pure water, that all the water molecules are free. And we know that chemical potential, it depends upon the free water molecules, the molecules that can move across a semi-permeable membrane. However, in this particular solution, now this is water and this is solution because we have added solute into it. In this particular case, say it's beaker A and this is beaker B. Now in beaker B, we have solute added to the solvent, and what has happened due to the addition of the solute, that its chemical potential has decreased. Why it has decreased, I have told you the reason, that when solute is added, the solute molecules, it depends upon their size, they are surrounded on almost all sides by certain number of water molecules. Let's assume that NaCl molecule, it is added into the water, it ionizes, and we get a sodium ion and a chloride ion. So in this case, all the chloride ions, they are surrounded on all sides, say 5 molecules of water. And similarly, around sodium, we have 5 molecules of water. So the negative end of the water molecule, it is attracted toward the positive sodium ion or the cation. And similarly, the positive ends of the water molecules, they are attracted toward this anion, which in this case is chloride ion. Now this is just an assumption, and just to illustrate. As you can see, each sodium ion is surrounded by 5 water molecules, and each chloride ion is surrounded by 5 water molecules. So that means that if there are, say, 100 molecules of sodium chloride, so 500 for each. 100 multiplied by 5, so 500 here and 500 here. 500 plus 500, we get 1000 molecules. So 1000 water molecules will get occupied. They will bound to these sodium ions and chloride ions. So the out of the total number of molecules, you can subtract these 1000 molecules, that they will not be free and they won't contribute, they will not contribute anything to the chemical potential of water. So a very simple concept. So the greater the amount of solute in a solvent, it decreases the number of free molecules, and consequently it reduces its chemical potential. So CP, or chemical potential, in both these beakers is very different. Here we have, so to say, 100% chemical potential. It's pure water, all the molecules are free. But here the chemical potential, in this case, it is decreased. Say we just assume that it is 90%, because we have 10% solute added to it. So its chemical potential is 90%. That is, it is low. It is lower than this one. So this is what happens when solutions are made, that the number of free solvent molecules, in this case water, it decreases, and this lowers the chemical potential. So now let's revisit our example of osmosis. So again, we take a beaker. So this is a beaker, and we have added certain amount of solute molecules to it. Say it is a 10% sucrose solution. Again, adding 10 grams in enough water to make it 100 ml. And then we take a tube. Let's give it a different color. It has a sufficiently large bore so that we can add. And then we take a semi-permeable membrane and we tie to its mouth. Now this is a semi-permeable membrane tied here. And now we add solution in this particular. Let's draw a stand, although there is no need for it. So this is the clamp which is holding this tube, and this is just the bare bones. Now we add solution to this tube as well, and say we have added to it 30% NaCl. That means 30 grams of NaCl have been dissolved in enough water to make 100 ml of solution. So we have NaCl. Now what will happen? We have two solutions. Now instead of pure water, we have two solutions. We have sucrose in the beaker. It's 10% sucrose. Obviously its chemical potential has decreased to a certain amount. And just to assume, as we saw just now, let's say its chemical potential has reduced from 100% to 90%. Similarly, in case of NaCl, its chemical potential has reduced or decreased from 100% to 70%, because 30% of solute has made its chemical potential 70%. So we have 90% chemical potential in the beaker and 70% chemical potential in the tube. Now what will happen? Osmosis will take place, and since this is a higher chemical potential and this is lower chemical potential, water molecules will move from a region of higher chemical potential to a region of lower chemical potential, and they will start moving inside the tube. So what will happen now, that the level of solution inside the tube, it will start rising. As the osmosis progresses, the level of solution rises. It might rise up to this point. Say it stops then. It might not stop, but let's assume that it stops. And when it stops, equilibrium has reached. So now we have considered two solutions separated by a semi-permeable membrane, one with a higher chemical potential and another with a lower chemical potential. Now say we do not want the water to enter into the tube. So what we can do, say we are able to insert, let's give it a different color. We are able to insert a piston inside this tube. So this is a piston that has been inserted. And if we do not want to allow water to enter the tube, what we should do, what's required? Obviously, we have to apply certain pressure here so that the water may not enter the tube. How much pressure? The pressure, it should be enough to overcome this difference in the chemical potential, 90 on one side and 70 on the other side. I repeat again, these values are just assumptions, and this is just to illustrate the concept. These are not actual values. So we have 90% chemical potential inside the beaker. Water is trying to enter the tube because the chemical potential is 70%, but we do not want the water to enter the tube. So to stop the osmosis or to bring it to equilibrium, we would apply certain amount of pressure on the piston, and that pressure should be enough to equilibrate or to be equal to the free energy which is inside the beaker or inside here. And how we come to know that we have applied that amount of pressure, that is, the piston will not rise. If the piston is rising, it means the pressure is not enough. So when the piston is not rising, it is neither going up or it's neither going down, because if we increase the pressure and it is greater than this chemical potential, the 90%, what will happen? That piston will start moving downwards. So it is neither moving up or down. That means that this pressure has made or raised the chemical potential inside the tube. Since it has applied certain amount of pressure, so its water potential has raised and it has become equal to the water potential of the beaker. So the movement of water inside the beaker and outside the beaker has become the same. This application of pressure has raised the water potential of the solution inside the tube. So what will happen if we increase the pressure? And if we increase the pressure, water will start moving outside. That is, its water potential will become greater. Now this is a positive pressure, and this positive pressure is adding to the free energy of this solution. Since this is a positive pressure, it is adding to the free energy inside the tube. And if we increase the pressure beyond this point, what will happen? That the piston will slowly start moving downwards and water will start coming out of this particular tube. That is, its chemical potential has become greater. Now, as far as the amount of solute inside the tube and the beaker is concerned, the number of solute molecules, the number of solvent molecules, it didn't change. But simply applying pressure. Pressure is a positive pressure, that is, we are providing energy, and due to that, we have raised the water potential inside the tube. So this was just to illustrate the process of osmosis, the process of chemical potential, the free energy that is present inside the solution. In previous example, we considered in the last video, it was pure water and solution in the tube, and now we have solution in both the containers, in the beaker as well as in the tube. So we have solution in both, but those solutions have different chemical potential or different concentration of the solute. So due to which initially, since the chemical potential inside the beaker is greater as compared to the tube, so water will cross the semi-permeable permeable membrane and it will enter the tube, and the water level or the solution level will rise inside the tube. What we did next, that we introduced a piston inside the tube, and we wanted the water level to remain the same inside the tube. That is, water may not enter from the beaker into the tube. So we had to apply certain amount of pressure, which is a positive pressure, and this pressure has provided certain energy to this solution inside the tube, and it has raised its chemical potential. And if we keep on applying the pressure, at a point will come that it will overcome the water potential inside the beaker, and the water will start moving outside the tube into the beaker of water. But as I stated earlier, the application of the pressure does not change the number of solute molecules or the number of water molecules, solvent molecules in both the solution. It remains the same, but simply applying a pressure changes the chemical potential of the container to which this particular pressure is applied. So these were few things about concepts about osmosis and chemical potential of water and its components that will be discussed in the coming videos. Thanks for watching, and see you in the next video.